Finally, another big update on this circuit. I added this section down here, which has been probably one of the most challenging sections that I've created so far. This is essentially called a watchdog timer. And this section here is the actual watchdog. And what that basically means is that this timer is set, and it goes off, say, every like 14 seconds. All right, but if it gets some input from somewhere else in the system, then it resets and it starts timing again to 14 seconds. So assumedly, if an input happens in the system more frequently than 14 seconds, then this timer actually never goes off. Now, if there is no input on the system and 14 seconds elapses, then this timer goes off, and that triggers this flip-flop over here. And the two LEDs here on the flip-flop indicate the state of the flip-flop. So this is the Q output, and this is the not Q output. So basically, a flip-flop acts like a latch. In this case, it's called a set-reset latch. And if it gets the set signal, which is the watchdog, then it sets the output on, and then the negated output goes off. And then if it gets a reset from somewhere else in the system, then it resets it to the off state. And these, again, invert. Now, why is that interesting? Well, that's interesting because essentially I can use that as a way to save the displays from burn-in. So one problem with Nixie tubes, and I assume that's also true with vacuum fluorescent displays, but I don't know that for a fact, but Nixies for sure, if they sit at the same digit for a long period of time, that digit can start getting a little bit of cathode bleed, and what will happen is that digit will never quite turn off. And so it's not good to have a Nixie tube sitting at the same number for a long period of time. And I thought, well, if you're not using the system, then, this tube is displaying the multiplier. It's never going to change. It's going to be set to whatever digit you set it to. It's going to sit there for a long period of time. So now with the watchdog timer, I can have the circuit determine that nothing is happening, and it can blank these two digits. Now, blanking this one actually ended up being really easy. The BCD, the 7-segment driver chip that I'm using, has a blanking input, which is active low. So as long as that input is high or has power, then the output can display something. But if you set it low to ground, then it will blank the output. So that one was actually really easy to turn off. The problem with the Nixie driver is the Nixie driver does not have a blinking input. So that was another really challenging part of this update. What I finally realized is that if we go to the truth table for this, essentially, if the A and B input both have a high, then the display will be shut off because it's not a valid binary coded decimal, since it only displays up to 0 through 9. That was also really challenging, though, because you can't just set both of these to high. I mean, if this one is set to high, it could have been an 8, right? And if this one was set to a high, it could have been anything from 4 through 7. So I had to get really creative on how to handle that. And what I finally realized after a lot of thought is that I could simply pass it through an OR gate. So an OR gate basically says, if the input is high, then we don't care, we'll take it. If the other input is high, we don't care, we'll take it. And if they're both low, then it's going to pass a low. So essentially, I can put my timeout on this auxiliary pin here, and then take my main input on the A pin here. And so it'll always represent whatever A is, unless the auxiliary input goes high, in which case it'll turn high. So that was quite a lot of work to figure that out. And it turns out I actually had an OR gate right here that had a couple gates that weren't used. So I was able to capture that with the yellow wires here, and I feed my 2 digits high here when I want to blank it. So that's really cool. The other part that was really challenging is actually the watchdog timer itself. So challenging, in fact, that I had to finally find a circuit simulation tool. So basically in this one, we have the test circuit here, which is the 555 timer watchdog. And then that's feeding the flip-flop over here. And this represents what the circuit is actually doing. So basically the green pulses are activity in the system. Say like as soon as you actually dial something, or actually even just move the dial here, consider that the green pulse. So as long as there's green pulses in the system, then the watchdog isn't going to do anything. But when there's a period of time, some configurable time period right here, that it doesn't recognize any pulses, then the watchdog will turn on, which is negated. So actually it turns off until it starts seeing pulses again. So it'll see pulses and it won't do anything until it finds a period of no pulses, and then it'll switch off. And then again, it'll turn back on as soon as there's pulses. So that's kind of cool. So it's kind of like a way to determine when there is or isn't activity, but it's hard to do something with that. So to do something with that, we have to throw it into the flip-flop. And the flip-flop basically says, as long as there is no activity, when we see this falling edge here, trigger the flip-flop, which actually stores the value here in the set output. Okay, and then as soon as we have activity again, it's going to reset, and it's coming back here, and we do something to the set output. All right. So what's kind of hard to fathom about that is how does that actually look in response to the input pulses in the system? And that's what the gray output up here is. So that's going to be our not output, our Q not output, which is up here. And basically what ends up happening is we'll have a signal right up until our watchdog goes off, and our watchdog doesn't matter what's happening here. We're going to stay turned off until we get some other new input into the system, which is the reset signal on the flip-flop. And that will cause it to reset, allow pulses to come through. And then again, if we have a period of inactivity, it's going to come down again. So this is actually what we're going for, because that high signal can feed into our blanking input because it's active low. So as long as it's high, we won't be blanked. And then when it goes active low, that's going to blank the outputs of the system, in other words, turning off the digits. So this was really hard to come up with, and that's what this circuit is here. And then there's one other feature that I added in, and that's when we're in the inactivity period, it would be kind of cool if there's some kind of an indicator that lets you know that you're in that inactivity period, because all of the displays are going to be shut off. But this circuit right here represents like a breathing LED circuit. And when we're in this period of inactivity, the breathing circuit comes on, and the LEDs here will go through fading in, fading out, as if they're slowly breathing. So they fade off. Now they'll fade back in. Now they'll fade off, etc., etc. Okay, so that's really cool, but I mean, is it doing anything? It says it's in the inactivity period. So if we give it some activity, what happens? Well, there we go. We dial. Before the video, I put a 9 into the registry. Did 9 times 1 is 9, so it just counted down to 9. And again, as long as we have no activity for a certain period of time, these will eventually blank off here. Ta-da! And we go back to our resting state, which will cause the breathing LEDs here. So if I give it some more activity, all right, so now it's on. And basically what we're seeing here in the oscilloscope is this is the charge on this capacitor right here. And if that charge gets fully charged for a certain period of time, it's going to cause the circuit to go into the wait period. So every time I give it activity, it bleeds out that capacitor charge and causes the timer to essentially reset. But if I give it no activity, you'll see it charges up. And as long as it's in that charging state for a certain period of time, we will then blank out the digits. Just like that. And when we give it a reset, it comes back on, Cap starts charging again. So it's all a timer here. As long as there's activity, before that reaches that timing period. So we can also, do something more interesting. We can go into programming mode. And when we're in programming mode, the LEDs are flashing to represent programming mode. And you see the cap never reaches a full charge because it's still being drained by the programming mode indicators. So that cap is trying to charge up, but it can't because we're still seeing activity in the system. Now, if I give it some multiplier, let's try like a 5, for example. So we do a 5 multiplier, put that into the multiplier. Now it's starting to charge up again. So if we do like a 1, have a 1 times 5, would be 5. There's 5, counts down. About 4. So that would be 20. 20 should show up on our counters here and count down. And as long as there's activity in the system, you see that cap is never charging. But as soon as that activity stops, the cap starts charging up, and then it reaches that timeout period, and our digits blank, just like that. And we go into our standby mode with pulsing or breathing LEDs. So that was super, super, super challenging. The last phase of that, of course, is like 13 seconds is a pretty quick timeout. I'll probably set that timeout to something like a minute or maybe 2 minutes or 5 minutes. The problem there is that the 555 timer doesn't really like to wait for a long period of time. So I might have to reset or change this to a different monostable oscillator that is okay with longer periods of time. So that's a bit of a drag. Might have to order one more component to swap that out. But the idea of it is totally working, and as demonstrated. And, the last cool thing is I wanted to have 2 more vacuum fluorescent displays that would kind of like oscillate as the clock is pulsing. That's essentially what that blue LED is representing there. But I don't really have a place to put those VFDs in the final solution. So I'm thinking about those VFDs were going to be powered by vacuum tubes, and that vacuum tube is just a flip-flop, and I'm using a flip-flop right here. So I'm thinking that I can replace this chip with a bunch of silly vacuum tubes, and I'll still get to have my vacuum tubes in the circuit, and they'll still be actually doing something. They'll be controlling the timeout period of the circuit. So I think that's going to end up working really awesome. And I suppose that's kind of the last step there. Yeah, working really well.